Hello everybody. So this video will cover one of scenarios of configurations you can use in order to harness the energy from your excited coil. There are many variations within the system, so I will go step by step to parts of it and explain a couple of things here, what you can and what you can't do. So we start with the obvious thing. So we had before used the diodes directly on the capacitor and charged the capacitor here, but it was not this capacitor, it was just a microwave capacitor which you could charge within under a second. It had only 1 microfarad, 2,500 volt. But here we talk about a complete different subject. We're talking about 450 volt and 1000 microfarad. So the system is literally 100 times, can store 100 times more power than the microwave oven capacitor. So this one's tracing 100 joules. If you charge it in 1 second, it gives you back 100 watt of power. So that's our benchmark. So I used that capacitor to make sure that I have a lot of range free. So I will not be able to charge it to the full value, but we will see that in a minute. I will explain now in details the setup and go through the components here on the table. It's my usual setup. You have, and I also use my usual amplifier, my driver. I have to use 2 DMMs, one analog and one digital. That becomes apparent a little bit later because there's so much RF there that this one is stalling right away with error messages and so on. So we have to go here, and later on when I switch it off and show the values of the capacitor, I can then use the DMM. I use here a shunt for the capacitor because it's highly dangerous, and I can tell you, I have tested it. It burns cables if you connect them. So here I use 1 kilo ohm, so that gives me a safety margin. So I can discharge it safely here. So we are using a second coil to pick up the energy from the first coil system. However, that is one of the scenarios I will explain here is you cannot, and I repeat, you cannot connect this coil directly to your first coil system. Why? Because it becomes then part of the network and will change your frequency altogether, and this system, this coil then becomes then part of the whole system, which means it influences the whole system. So if we want to take energy out from the primary into the secondary coil system, we have to be independent. How can we do that? Now that is one example I want to show you. You do that only by picking up the signal via a diode. Very important. I will put a drawing on here. You will see that. It's very, very simple. However, that's the only link here, only pulsed positive into the secondary coil system. And there, it's on a ferrite here. I use also a bifilar winding. Why? Because a bifilar winding is frequency independent. That means I do not need to tune that, and any frequency I put through, I go out here. However, this coil would be frequency dependent. It might be more efficient here to add a capacitor. I will do that at a later stage. At the moment, I use it directly. I go in here to a manufactured full bridge rectifier. I'm using Moore's, I'm using fast recovery diodes, the fastest you can get. However, they're still not fast enough. We talk about that a little bit later. a capacitor, I cannot use my air capacitor anymore, because at the value I'm getting up here it will spark instantly. So I use them, 3 of them. You have seen them before. They're door knobs. They're 40 kilovolt rated each. That means I have 120 kilowatt range here. I'm using a spark gap at the moment not connected. That means I have the connections of both electrodes shunted. So that's a straight connection that goes to ground, and it does not go to normal ground. That's another example. It has to go to a specific ground you have to build. In my example, my negative ground on the south side, which I connect also via a variable resistor, which is a carbon wire resistor, which is variable, which can be adjusted here. Also very important to use that. So the grounding side, so I come in here to the coil via the diode. However, my return signal goes to ground, but to a different ground, and that is also very important. This ground, and let me remind you on copper NAS's design, and that is not the only one. A lot of others have to do the same, especially when you would talk about static energy. You have to use 2 different kind of grounds. One ground has to be negative and one ground has to be positive. So the negative side would be the side where you connect actually to a liquid fluid system. Liquid system can be a water line. Best would be iron, not copper. But if you have nothing else, you can use your copper wire where the water is running through. So on the positive side, it can be copper. So here I use my ground system I have in the garden. It's copper based. You cannot use as your standard grounding system copper. Why? Copper does distribute energy and does not give you the energy we require for the system. I will show that later. Now system is running now. You can see the waveform here. At the moment, as you can see, it charges up to 15 volt. And one important part of it at the moment is, you see here, hope you can see that, let me zoom in a bit. It says 1 2 watt, and yeah, on the input side 443 watt. Bear in mind that it's now that the negative side of the coil is now directly connected to earth, so it's draining your potential here. Don't have that much anymore. But the interesting part is, so we are at 17 volt here. Now let me drain that. Now have a look. Have a look what happens if I shunt, or if I actually shunt the capacitor. What happens here with the current? It goes up. So you see here it's completely shunted. I have it full stop. I cannot go lower than 8 volts. So 8 volt I have still in the system and it's completely shunted. So that means 8 volt can maintain a 1000 ohm resistor here at 8.8 volt, but already at 220 milliampere. So that's quite a lot. That's a force of, that would be almost 2 watt. So we have here 8 volt and 1000 microfarad. That doesn't give you 2 watt. So it's lower than what we have. If I release it again, I go back to 40 milliamp and only 1 2 watt in power output. And if I shunt here and so on, it has no influence on the side here. Very important. See if you can see that. So if I shunt now, it makes no difference if I shunt that now and it goes down to 8 volt. The waveform does not big change. Okay, from 345. Okay, changes around 100 volt when I when I shunt. However, the power is much higher than when you go in. But makes no influence here. So let me increase a bit the voltage. But you see here, I have a lot of power going in, and it's not much coming out here. Okay, charges up only 22 volt. For this is almost 7 watt already going in. And here, if I take that, it's nothing coming out. Even tuning different frequencies doesn't change much, because it's connected to ground. It is very, very difficult one, but it's almost nothing. And as you can see here, 25 volt at the moment charged. If I shunt that down, it holds it at 9.6 volt, even shunted. Current does not change, but it's about 3 watt. So this is one major importance for your coil system. You're connecting a secondary system which is independent from a load you're putting into this first system. So it has to steal its energy from somewhere else. At the moment it cannot, or it hardly can. It tries to, but it is not working that well. Up to the frequency which is more appropriate later. So the resonance frequency is around 32. Something like that. Still 2 watt. Nothing changed. Let's see if we can improve on that. Now I have disconnected the shunt to the ground. There is no grounding connected anymore except the grounding to the secondary coil. So I'll let that run. You see 3.9 volt, 100 milliampere, it's 390 milliwatt. I have over 1 kilovolt on the output side. And this is a waveform. Looks different now. Let's see if we can change that. I think that is quite good. .5, yeah, that was the best value. Here we go. So here we have set 3.9 volt. Of course, it's not charging up much. So let's increase a little bit the current. Now it's getting a little bit hectic, 5 volt. So I probably have to get a little bit down. Oh, this one is already not happy with me. With 6 volt and 130 milliampere. This one doesn't work anymore, so I have to switch over. I have to align the scaling. All right. Okay. Now you can see something interesting here. That will become a little bit more apparent. What we see here, let me stop that for a sec. Let me zoom in to show it to you in a little bit more in detail, because that's an important part. It's not so strong defined now at 6 volt, but when we go up to 15-20 volt, this will become extreme. What is it? We have a waveform which is increasing, and at the highest value goes down and explodes if you want. And when it does, it ripples, and that ripple goes over to the secondary coil, and it has also a ripple at that moment on that side. So the problem is that this is only a small fraction of time, whereas in the rest of the time nothing really happens. So that is your current. So this both values, if we zoomed on that bit in, let's see that. So that's your small window. At this small window something happens, and the rest of the time literally nothing happens. So we have a tremendous amount of power here, but that is so brief that the system can't handle it. That means it goes unused in the system, but the system is too reluctant or is too slow to take advantage of it. So we have to take, or the system is taking the average of these peaks and what's in between available, and that is providing the level of energy we're gonna have. Now if I increase a bit, so we are at the moment at 12 volt, 120 milliamp. Let's do some measures here to show you that. So we have 30 milliamp So we have here 30 milliamp as minimum when I started it on calculation. Or let me do that again. Calculation. So it starts again. It starts with 660 and goes up to peaks to over 1 amp. That means we're starting low with 50 watt at peaks. Bear in mind these are the brief moments. This is not a continuous value. And then it goes up to 200 watt. Voltage is fairly the same. So we have about 50 volt at the moment in. Let me shunt that. See, if I shunt that, same thing, my current goes up dramatically. Goes up to 6 amp. It holds it here around 20 volt, then it goes up again to 50 volt, 40, 50 volt. I'm at the moment at 12 volt and 130 milliampere. Okay, now let's increase it a bit. I'm now at 20 volt and the needle is raising here strangely. Normally it should stay at one value, it shouldn't go down. Maybe it's influenced by the magnetic fields. So 20 volt and 20 milliamp. Let's get that down a bit. Now let me show you how it looks like. That is the wafer I was talking about. Yeah? It starts small, it's increasing, and here it explodes when it collapses and it goes up again. This is a negative waveform, a negative resistance chart you would expect from an energy system we are talking about, where we're harnessing more energy than from system. So what the coil system is providing is only potential, no current, almost no current. The current does not come from my coil system. The current comes from the ground. That is very important to note. Without ground, I have no current. So if I want to have that in a different fashion, I would have to build something completely different. But this is a system where most of the systems actually work in that way. You provide potential via your coil system and you provide current from the ground. However, the ground current can only be harnessed under specific conditions, and they are not simple to replicate. I have started with that subject already, with my Earth battery. I will continue on that. There will be new specific coil systems I'm gonna use, and they have a huge impact. They will not be used in a traditional fashion. We are not harnessing any radio waves here. We are connecting to the ground and being part of the energy which is in the ground. That's what we're doing. So that's the Earth's magnetic field we are harnessing here. We are tuning into it, if you want. We're gaining the energy from the capacitor, the large capacitor which is called Earth, the negative ground, and we are taking this energy out of here. So that gave you a brief introduction, and I will continue in my next video with a couple of other scenarios.